Have you ever found yourself tangled in the complexities of programming concepts like lazy evaluation and monads? It can be quite a challenge, right? If you're diving into these topics, you're in the right place. Today, we're exploring whether lazy evaluation can be implemented by a monadic type in JavaScript. I totally get it. Trying to understand lazy evaluation alongside monads can feel overwhelming. You're not alone in this struggle. Many developers face similar questions when they start exploring these advanced concepts. Here's the specific question we're tackling today. One user asked, can lazy evaluation be implemented by a monadic type in JavaScript? They shared their attempt at creating a lazy type and expressed confusion about its behavior. Sound familiar? Let's break it down together. So what's the issue here? The user's implementation seems to trigger evaluations prematurely, which raises some important questions about the nature of lazy evaluation in strictly evaluated languages like JavaScript. Let's explore this further. And stick around. By the end of this video, you'll have a clearer understanding of lazy evaluation and how it interacts with monads, plus some practical insights you can apply in your coding. To address the user's implementation of lazy evaluation with a monadic type, we first need to clarify the concept of lazy evaluation. Lazy evaluation means that expressions are not evaluated until their values are needed. Next, the user should ensure that the lazy type correctly encapsulates the thunk. A thunk is a function that takes no arguments and returns a value. This is crucial for achieving laziness. Now, let's examine the lazy.fold method. This method should apply a function to the accumulated value and the result of the thunk. The user needs to ensure that the thunk is only executed when needed. The user should also consider the lazy.join method. This method should not trigger evaluation prematurely. Instead, it should return the inner lazy value without executing it. Finally, the user should test their implementation with various functions to ensure that the lazy evaluation works as intended. This includes checking if the values are computed only when accessed. Fun fact, did you know that Haskell was designed with lazy evaluation in mind from the very beginning? It's fascinating how different programming languages handle evaluation strategies. Now, let's look at the answers provided by other users. This user suggests that implementing lazy evaluation with a monadic type depends on the definition of lazy evaluation. They propose creating a delay type that functions as a monad. However, they note that using a type like A to delay B implies that the argument A has already been evaluated. Instead, they argue for a structure like delay A to delay B. They also mention that there are different ways to convert expressions into monadic style, specifically call by value and call by name. This concept is explored in Phil Wadler's paper on comprehending monads. The user suspects that using a call by value translation with a delay monad may lead to slight inaccuracies, suggesting a shift towards a call by name translation for better results. Now, let's shift our focus to a different response. In this alternative approach, the user points out that the lazy join function should be modified to prevent immediate evaluation. They suggest wrapping the evaluation in a lazy function to maintain laziness. The user also emphasizes that a complete lazy implementation should include sharing results to avoid reevaluation, which necessitates mutability and works best with pure functions. That's it for that response. Let's explore another one. In this alternative approach, the user suggests simplifying the lazy type by removing unnecessary thunk wrappers. They emphasize that the join function needs to properly handle the unwrapping process to avoid premature evaluation. Additionally, they point out that the monadic return function should align with the data constructor for consistency. The user also introduces a memoization technique within the runLazy method to prevent reevaluation of results. They share their code modifications and express enthusiasm for further exploration of lazy evaluation and monads. Here's a takeaway. While you can implement lazy-like behavior in JavaScript, True lazy evaluation, as seen in Haskell, is not straightforward due to the language's strict evaluation model. Keep experimenting and learning. And there you have it. We've explored the intricacies of lazy evaluation and monads in JavaScript. Keep pushing your boundaries in programming, and if you found this video helpful, don't forget to subscribe for more insights and tips.